Hi everyone, welcome to our next video for the week 4 series, where we talk about confidence intervals for a mean. There are a few assumptions that we make when we're constructing these confidence intervals. In your textbook, it's safe to assume that these conditions have been met, but if you are a researcher that's collecting and analyzing data out in the real world, this is something you should check before you find the confidence interval. So there are a few things. First, and this is true for everything we're talking about in inferential statistics, we are assuming that the sample is a type of random sample. And you'll remember from the beginning of the summer course, we talked about several types of random samples. Any of those random samples works, but it needs to have randomness as its main generator. We also know the population standard deviation for the type of sorry, confidence interval we're constructing today. And we are assuming that either our sample is bigger than 30, bigger than or equal to 30, or we are explicitly told that our population is normally distributed. So the middle condition, we know the population standard deviation has to do with knowing how spread out the data is and what that tells us about how wide our confidence interval needs to be. The last condition has to do with sampling distributions and the central limit theorem. We know that in order for that sampling distribution to be guaranteed to be normal, we need a large sample size, or the original population of raw data needs to be distributed. So that last condition is coming from the central limit theorem. Okay, so let's talk about how to find the confidence interval. I'm briefly going to go through how to find it by hand, but I do not expect you to do these calculations by hand unless you really want to. I really just want you to see where the numbers in your calculator are coming from. So to do this by hand, the first thing we're going to do is read that problem. We're going to pick off the population standard deviation and identify or calculate the sample mean. Sometimes they'll give you the sample mean directly. Sometimes they'll give you a list of raw data and ask you to calculate it. Next, you're going to find the z-score that corresponds to our confidence level. So that has to do with the standard normal distribution. So we're dealing with a sample of a set size, and we know when we're dealing with samples and sample means, we're looking at sampling distributions, and that we are assuming that our sample is large enough or that the original data is normally distributed so that our sampling distribution is going to be. Things are normal, we know we can describe them with the standard normal curve. So we know the standard normal distribution is normal or bell-shaped. It has a mean of 0 and a standard deviation of 1. This is something we saw, I believe, last week. When we build our confidence level, we're going to be told how confident do we want to be that our range of values is going to contain the thing we're trying to estimate. So for example, sometimes they'll tell us we want a confidence level of 95%. I want to be 95% certain that the actual population value is in this range. So what I do is I mark off the middle 95% of the curve. I make sure that it's centered about that 0 value so that this is 95%. And then I need to find those z-scores that form the boundary for that middle 95%. You'll notice here it says z-score. Because the standard normal curve is symmetric, I know that both of these z-scores are going to be the same size. They're just going to differ by a sign. So typically we're only going to look up this value down here, which will be negative, and then we're just going to drop the negative sign. Once we have that z-score that tells us where that confidence level falls in a standard normal distribution, we're going to use it to calculate the margin of error. You're going to see your textbook call that the EBM, the error bound for the mean. The formula for that is actually pretty familiar. We see that z-score we just found in step 2, z alpha over 2, and then times the standard deviation for the sampling distribution. The population standard deviation for the raw data divided by that square root of n. So all we're doing is taking a z-score and multiplying it by the sampling distribution standard deviation to calculate our margin of error. Once you know what your margin of error is, you're going to use it to construct the interval by adding and subtracting it to the sample mean. So the sample mean minus that margin of error is the lower end of your confidence interval. And the sample mean plus that margin of error is the upper bound for your confidence interval. So we know if our confidence level is 95%, that we're 95% certain that population mean is somewhere between this lower number and this upper number. After you've constructed this numeric statement, you should write a sentence that interprets that estimate in the context of the word problem. So you're just going to summarize what you found in a sentence. We know with 95% certainty that the population mean falls between the values of blank and blank. Okay, so my assumption, most of you are not going to want to do this by hand. So let's talk about finding that z alpha over 2 really quick, and then we're going to move on to how to do it on your calculator, which is, I'm assuming, what you guys are interested in. To find that z alpha over 2, we're looking at that confidence level, that's the area in the middle, just like I drew on that previous slide. That alpha that we're talking about is 1 minus the confidence level. The alpha is the amount that's left for the tails once we've centered that confidence level in the middle of the standard normal curve. We're then going to cut that alpha in half because we know that we have 2 tails. So for example, in that previous slide, our confidence level was 95%. So we knew that this was 95%. So when I come to find alpha, alpha is going to be 1 minus 0.95, which is 0.05. And then when I get to step 2, I'm going to take that alpha and divide it by 2. 0.05 over 2 is going to be 0.025. And that is how much area is in that lower tail or upper tail. So here's our middle 95%. This tail here gets 2.5%, and this tail here gets 2.5%. We're then going to use table E or a calculator or computer to look up the z-score for this boundary down here. What is that boundary? So for example, if I wanted to use a TI-84 for this, I would pull up my TI-84. Ooh, nope, didn't want to do that. And we're going to go second vars. And I don't think my second works. So let's try that again. Second bar is to get our distribution menu. And I'm going to go down to inverse normal. And it's going to ask me for the area. I know the area in my tail is 0.025. And this is standard normal. So mean is 0, standard deviation is 1. And it gives me negative 1.96 if I round it. I'm going to drop the negative because I know this lower is negative 1.96. The upper is positive. So our Z alpha over 2 for a 95% confidence level would be, whoops, sorry, 1.96. You will notice that we're going to round our z-scores from the calculator and computer to 2 decimal places because that's what table E works with. If you were to look this up in table E, you would actually need to go to the center of the table and you would need to look up this information here. You would need to find the number that is as close to 0.0250 as possible. And then you would read up to the top of the table and over to the side of the table to find those pieces of your z-score. Again, I don't expect that you're doing this. And if you are in fact using a calculator, there isn't any point in finding this Z alpha over 2, but it is good to see where it comes from. The upside for us is if we're using technology, the calculator is going to do that behind the scenes. So if you're using a TI-84, you're going to press Stat, and then you're going to go over to the Test menu. You're going to go down to option 7, which is the interval. So this is an interval for the mean, and we're using the standard normal curve. And you're going to see a bunch of prompts for information. And you should fill in those prompts as directed on the calculator. You will notice that there is an option. Pull up my calculator here. Stat, test, option 7 for data or statistics. So statistics is if they gave you that sample mean in the problem. Data is going to ask for a list. Where did you put the raw data from the problem? So if you're doing a confidence interval for the mean and you're given a list of sample data, put that in a list first and then go through this process. Once you've filled in that information, you're just going to press select, calculate, and then enter, and it will spit out your confidence interval in that ordered pair format, which is what your book's using. It's going to spit out the lower bound of your confidence interval and the upper bound of your confidence interval. Again, you're going to see me write it this way. Lower bound is less than the population mean is less than the upper bound. The third way, which is the lower, not the lower bound, sorry, the sample mean plus or minus the margin of error is typically only used if you're calculating by hand. Since we're not calculating by hand, you're not going to see me use that notation. If you're on GeoGebra, it's a similar idea. You're going to use the following command. There are 2 different commands depending on whether you have a raw list of data or you have that sample mean already calculated. If they gave you the sample mean, you're going to use Z mean estimate and then sample mean, population standard deviation, sample size, and confidence level. If you're given a raw list of data, you're going to use Z mean estimate, list of sample data, and then the rest of that information. So population standard deviation and confidence level. A reminder that when you enter a list of data, curly brackets, and then number, comma, all the way down to your last number and then close the curly bracket. So that's what would go here for that list of data. You can also give that list a name. You could say A equals on the previous line. And then when you call Z mean estimate, you would just type the list name here, A comma. That's typically what I do, as it leaves the function call less cluttered on the screen. But either method works and you should get the same answer. If you are asked for that margin of error, that error bound for the mean, once you have your confidence interval, you can just take that upper limit and then subtract the sample mean from it. So upper bound minus sample mean will give you that error. I'd like to do 2 examples really quick to show you what this looks like. So example 8.2 says, suppose scores on exams and statistics are normally distributed with an unknown population mean and a population standard deviation of 3 points. A random sample of 36 scores is taken and gives a sample mean of 68. Find a confidence interval estimate for the population mean exam score. Find a 90% confidence interval for the true population mean of statistics exam scores. So I know I'm being asked for a confidence interval. That was the first thing that I saw, find a confidence interval. So I know that's what my problem's about. And then I'm going to pick through information that I'm given. So I know that these exam scores are normally distributed, which is great. We know the population standard deviation is 3. So sigma equals 3. We also know that we took a random sample of 36 scores. Our sample size is 36. So even if we weren't normally distributed, our sample size is big enough that we still meet that requirement to use the central limit theorem. And we're told that the sample mean is 68. So X bar is 68. That's going to be the center of our confidence interval. And then down here, they say a 90% confidence interval. So they're telling us our confidence level is 90% or 0.90. So that feels like a lot, but now that we've identified the relevant information, the calculator is going to do that heavy lifting for us. So let me copy that information down, and I'm going to pull up my calculator. So we know that sigma is 3, n is 36, x bar is 68, and our confidence level is 0.90. So let's erase the rest of this now that we've identified what we're looking for, so I can pull up our TI. I'm going to do this first example on the TI calculator, and then the second example on GeoGebra so we can see what that looks like. We'll go back to stats here. And then we're going to enter 3, X bar is 68, sample size is 36, and confidence level 0.90. And you'll notice it gives us that pair of values, which is the lower and upper bound of our interval. And then it gives us back that sample mean and standard deviation just to be sure that we did this correctly. So our confidence interval is 67.178 to 68.822. So let me minimize that calculator, and we're going to do our very last step, which is we should summarize what this tells us in the words of the problem. So we can be, let me type this so I'm not giving everyone a headache. We can be 90% confident that the true mean exam score is between 67.178 and 68.822. So that's basically it for finding that confidence interval. The heavy lifting is the beginning and the end, identifying what you're being asked for and the information that you're given. And then the end is interpreting what that calculator spits out in a way that makes sense in terms of the information in the problem. So for this problem, we knew that we were talking about exam scores on a statistics exam, and we are trying to estimate that true mean for statistics exam scores. So we know that we can be 90% confident that that true mean exam score is between 67% and 68.8%. Okay, let's try a slightly different one. So example 8.3, the specific absorption rate, SAR, for a cell phone measures the amount of radio frequency, RF, energy absorbed by the user's body when using the handset. Every cell phone emits RF energy. Different phone models have different SAR measures. To receive certification from the Federal Communications Commission for sale in the United States, the SAR level for a cell phone must be no more than 1.6 watts per kilogram. The table on the next slide shows the highest SAR level for a random selection of cell phone models as measured by the FCC. Find the 98% confidence interval for the true mean of the SAR rates for cell phones. Assume that the population standard deviation is 0.337. So we're given a little bit less here in terms of summary values. We're told we want a 98% confidence interval. So I know I'm finding a confidence interval for the mean, and I know my confidence level is 98%, so 0.98. I'm also told down here that sigma, our population standard deviation, is 0.337. The other two pieces of information we need are a sample size and a sample standard deviation. The upside is we know that our calculator can do all of this for us. So let's go ahead and pull up GeoGebra and start entering that information. So for GeoGebra, we know that the very first thing we have to do is enter a list. We need to get all of that data in list form. So that's the first thing I'm going to do. And I'm going to give this list the name A in curly brackets, and then I'm just going to start typing those values. So you can see that I have the list of values from that table in GeoGebra. And now we're going to go ahead and start doing that calculation for the confidence interval. So we know that we want Z mean estimate. And you'll notice when I start typing, it pops up. And let me make this full screen so we can see. Oops, there we go. It wants list of sample data, sample standard deviation, or population standard deviation, sorry, and confidence level. So list name, standard deviation, confidence level. So we know that our list name is A. We know that our population standard deviation is 0.337, and we know that our confidence level is 0.98. And you'll notice that GeoGebra does a similar thing to the TI. It spits out a pair of values. I am going to round them to 3 decimal places, just like I did that last set. So we know that our confidence level is from 0.881 to 1.167. So we can be 98% confident that that true population mean for the SARS for cell phones is between 0.881 and 1.167. And if you'll hang on just a second, we'll go back to that last slide, and you'll see that we want the SAR level for a cell phone to be no more than 1.6 watts per kilogram. And 1.6 is way outside that range for the mean SAR. So the cell phones in this table have an average SAR that is less than the 1.6 required. And we expect, based on this sample of cell phones, that the mean for all cell phones is between this range, which is well below that 1.6. There is one other thing we can do with the information we have about calculating confidence intervals. If you are a researcher and you know what your margin of error needs to be, you can use that formula for the margin of error, the error bound for the mean, to work backwards and get the sample size. So let's take that equation for the error bound for the mean. Margin of error is z alpha over 2 times sigma over the square root of n. And we're going to solve it for n. We know to get rid of square roots, we have to square everything. And then we're going to multiply both sides by n, divide both sides by that error bound, and we end up with the sample size is z squared times sigma squared over the margin of error squared, where z is z alpha over 2. This is the one instance where even if you're using a calculator to do confidence intervals, you might need to look up that z alpha over 2 value on your calculator or table. Let's go ahead and do an example really quick so you can see what this process looks like. A warning before we do that. More often than not, this equation, because it is a fraction, is going to produce a decimal answer. If your sample size is a decimal, you should always round that up. We always want one more person than one less person. If we have too few people, we're not going to get the appropriate margin of error. It's better to have an extra person than not enough people. Okay, so this example says the population standard deviation for the age of Foothill College students is 15 years. If we want to be 95% confident that the sample mean age is within 2 years of the true population mean age, how many randomly selected Foothill College students must be surveyed? So first read, it's how many randomly selected students. So they're asking me what is my sample size? What should my sample size be? Looking through it again, I'm going to start picking off those numbers. So population standard deviation is 15 years. So they've just given me sigma. And then it says we want to be 95% confident. So our confidence level is 0.95. And it says that we want to be 95% confident that the sample mean is within 2 years. So they're telling us that our margin of error, our error bound for the mean, is 2. When we construct our confidence interval, we want it to be the sample mean plus or minus 2. The question is, how many people do we need to make sure that error bound is equal to 2? So we're going to go ahead and use that formula We know that the sample size is that Z alpha over 2 squared times the population standard deviation squared divided by that margin of error squared. Now we have two of those three things. We know the error bound is 2. We know the sigma is 15. It's that Z alpha over 2 we need to look up. So off to the side here, I know that if my confidence level is 0.95, that my alpha is going to be 1 minus that, which is 0.05. And then I know alpha over 2 is going to be half of 0.05, which is 0.025. And then we're going to use inverse norm, 0.025, 0.1, because we're looking at the standard normal curve and the area in that tail is 0.025. If you're on GeoGebra, it's inverse normal and the mean and standard deviation come first. So 0.1, 0.025. I'm going to pull up our calculator and do that really quick, but we have already seen that. So second bars, inverse normal. And you can see we did that earlier, 0.02501 and negative 1.96. And we know we dropped the negative sign. So we know that Z alpha over 2 is 1.96. So let's go ahead and plug those values into this formula. So on our calculator, we know we're going to want to do 1.96 squared times 15 squared divided by 2 squared. Let's pull that over here. So Z alpha over 2 is 1.96 squared times 15 squared divided by 2 squared. And when we do that, we get 216.09. So we know that our sample size needs to be 217. We know that if we have a fractional value, we need to round that number up. Okay, if you have any questions, feel free to contact me or drop by my office hours on Tuesday or Thursday. I know this can seem a little intimidating, so take a deep breath. Remember that most of the questions I'm going to ask are about confidence intervals, and that calculator is going to do heavy lifting. So really this week, I want you to focus on reading those word problems and being able to pick out what it's asking you for and the information that it's giving you and labeling that information appropriately. That's going to be the bulk of the statistics moving forward, looking at word problems and parsing them. All right, I hope you have a good rest of your week, and hopefully I will see you in the next video.